SQL Server Index Internals. My name is Tim Chapman. I am a field engineer with Microsoft. And again, thanks everyone for coming to this ludicrously early session. I appreciate it, and hopefully we won't disappoint today, okay? I'm not going to use the podium and stand up. This is a session with a lot of demos, and so I don't want to stand up, walk around, then do demos, and that context switching isn't all that much fun. So I'm just going to sit down. Hopefully that's okay. Please silence your cell phones. Text as much as you'd like during this, but try not to answer any calls if you don't mind. I would appreciate it. Once I've done, go to the Past Summit/evals website and fill out an evaluation for me if you don't mind. I'd love to hear how I can be a better presenter, what I could add, what didn't make sense, any criticism or anything you have to say. I would love to hear it. So please go fill that out. A little bit more about me. I am again, a field engineer with Microsoft. I am a Microsoft Certified Master at least till the end of the year, or whenever they decide to officially retire it. I guess I'm an MCM for life, or however that works. I'm on Twitter sometimes. My handle is Chapman. I tweet more during events like this, but sometimes I do blog. I do blog on the MSDN site. I also blog on the PFE blog, which I have a link to at the end. So why are you here today? Index structure familiarity. I'm going to dig into index structures today. I'm going to use some DMVs maybe you haven't used before. I'm going to use DBCC page. I'm not going to use a debugger because most of what we're going to look at today is not really needed for a debugger, right? But we're going to have some fun with DMVs, have some fun with indexes. If you have questions, please ask them. This is loaded with content, so if towards the end of the session I get strapped for time, I may ask you to hold your questions to the end, just so we can get through all the content. But while we're going, please feel free to ask questions. For those of you in the back who have questions, we have a microphone here, so feel free to come up and speak into the microphone if you don't mind. If you don't want to ask a question on the microphone in front of everyone, please come up after the session, and I'm happy to answer any questions you may have. All right? So let's get started. First and foremost, heaps. Now, a heap isn't actually an index structure. A heap is a table without a clustered index. In SQL Server, there are two types of tables. There are heap tables, and there are clustered tables. Okay, a heap table just means that table does not have a clustered index on it. So it's unordered. We don't maintain any type of order for a heap. Wherever we can fit a record into the heap, we'll fit that record in there right wherever we can. We use a couple of different allocation pages to figure out, number one, all the pages associated with a heap. We use an index allocation map to tie all those heap pages together so they are one uniform structure. And whenever we need to insert a record into a heap, we'll go and look at a PFS page, a page free space page, to basically say, hey, for this page, how full is it? Can I fit this record onto this page? So we'll scan first, we'll look at a PFS page, keeps track of, I think, 64 meg worth of allocation. We'll find a page that we can insert into. We'll go insert that record onto that page. Heaps are great for inserting data really quickly into a table. So for ETL processes where I just need to load data in, they're great for that. Typically for production level environments, they're not that great. Because they are unordered, our only facility to access them is we have to scan them, unless we have other non-clustered indexes on the table. So anytime we have to look up data in a heap and I don't have a non-clustered index or any other index structure to facilitate it, then I have to scan that heap. The bigger that heap is, the longer that's going to take, the slower our queries are, the slower our applications are, and the fussier our end users are, right? Also, you can run into something called heap fragmentation. So if, for example, I have a variable character column on a table, and the data in that column expands so that that row no longer fits in that page, we have to move it. Whenever we move it, we keep track of where that record was with something known as a forwarding pointer. Okay? Whenever we have to scan that table, we'll see that that forwarding pointer points to a totally different page, and we'll have to skip over to that page to get that data. So that's a type of heap fragmentation. In earlier versions of SQL Server before 2008, maybe R2, don't quote me on that, maybe just 2008, The way that we remove heap fragmentation is we create a table with the same type of index structure, or not index structure, same type of structure, move all of our data over from our heap to our new heap and rename it. Now in SQL Server 2008 R2 and beyond, we can use an alter table rebuild statement to get rid of that heap fragmentation if you have heaps, right? In most cases for your production level environments, unless it's a special edge case, you're going to want a cluster table just because we maintain that order. There's a little bit of extra overhead in maintaining that order, but the benefits typically far outweigh the drawbacks. Okay. On to index structures. Today I'm going to talk about clustered and non-clustered indexes. We only have 75 minutes, so I can't cover other types of indexes like XML indexes, spatial indexes, new hash indexes in Hackathon or online OLTP, super fast OLTP. So we're going to focus on, clustered indexes and non-clustered indexes. And my guess is that in 95% of your cases, those are going to be the indexes that you're going to deal with on a daily basis anyway, right? A clustered index. We implement this as a B tree structure. So this is a sorted data structure, and we have to always maintain logical order of the structure. We don't always have to maintain physical order, physical contiguous structure for this, right? But we have to maintain the logical order. Well, what does that mean? It means that whenever I have a record that I need to insert into a table, based on the key, whatever I define that key is, okay, whatever column or columns I define in that clustered key, that particular record has to be inserted into a particular page, wherever that page is. Okay, so we have to maintain that logical structure. Now, once we find that page, we don't necessarily have to insert that row on that page in order, right? We don't maintain ordering of records on a particular page. We store records on an 8K page, just as a little bit of background. We have something on the page known as a slot array. We maintain that slot array in ordered structure, and what that slot array is just basically an array of offsets that so we know where a record begins and where it ends, but it would be a little bit prohibitive for us to maintain the records on a page in a given order. But we always have to maintain the logical order. Now, I mentioned before that we have two types of tables, right? We have a heap table and a clustered table. Whenever I take my heap, or whenever I create a table as a clustered table, that index becomes the actual table itself. Okay, so I create a clustered index on a table. I'm basically creating a new structure, moving all the data in my table over to that structure, and we're maintaining that order of that data based on the key. Okay, that's why you can only create one clustered index per table. Okay, you can't order a table in two separate ways just because there's only one way. That clustered index is the table, and there's only one way to order it. Okay, and we always implement a clustered index as unique. Whether you define it as unique or not, we have to maintain it as unique under the covers. So if you create a clustered index and you do not define that clustered index as unique, we'll actually maintain something under the covers called a uniqueifier. And basically that is so that if you did happen to insert a duplicate value into that particular index, we would be able to differentiate between those duplicate values. Okay, it's just like we seed it at 0, and then we'll implement it or increment it for additional values. So here's what a clustered index structure looks like, roughly. Okay? We always have a root page, and that root page is always a single page. Unless it is an allocation order scan, all index access is going to start at that root page. And that root page essentially contains values of the next intermediate level page. So we don't always have to have intermediate level pages. There's always going to be a root page and one or more leaf level pages. So whenever I start to traverse any sort of access method on this index, I'm going to start at the root. Make sure it's working there. I'm going to start at the root, and I'm going to say, hey, I'm looking for the last name Chapman. Where's Chapman at? Well, the root is going to contain records that's going to point to the intermediate level pages. So it's going to say, hey, for this particular value, you need to point to this intermediate level page. It's not necessarily going to contain all the columns, and it doesn't contain all the columns. And depending on how we define our indexes, that defines what column values we actually store in the root and intermediate level pages. But when we get to the root, we traverse it, we get to the intermediate level page, we say, hey, where is Chapman? We know that we're at the intermediate level page. We're not quite at the leaf level because in a clustered index, Once I hit the leaf level, because my table is the clustered index, we have all of the columns in the table. Okay, a clustered index always contains all the columns because it is the table. So looking for Chapman, say we're looking for the value 199, okay, instead of the value Chapman. So I'm going to come to the root and say, hey, I have 2 intermediate level pages. I'm looking for the value 199. Which intermediate level page points to 199? It's going to say, we're going to go to this intermediate level page. Okay? Once I get to this intermediate level page, I'm going to say, hey, which leaf level page contains the value 199? And assuming that 199, the column that we're looking in, is our clustered key. Okay? Ask this page, and it's going to contain a row for these pages down here. So it's going to say, hey, you're looking for 199, come down to this page. Once I reach this page, I have my record. And that record is going to contain all of my columns in the table. So that's what an index traversal looks like. We start at the root, ask the root, where do we go from here? Then we get all the way down to the leaf. And once we hit the leaf on a clustered index, we have all of our columns. Okay. Questions? Okay. On to non-clustered indexes. Let me make sure. Okay. On to non-clustered indexes. These are also B-tree structures. Okay, just like a clustered index. Same type of structure. The main difference is that in a non-clustered index, once we hit the leaf level, the columns at the leaf level are only the keys in the table that we define that index on. Okay, so say we have a non-clustered index on the last name Chapman. We will store the column last name in our non-clustered index, and we store it in sorted order. We maintain it in logical order as well. We also will have a pointer back to the base table. We always have to have some sort of pointer back to the base table. In the case of a heap, we uniquely identify rows in a heap with it's called a row ID, a RID. Okay, it's an 8-byte value. If it's a clustered table, we will contain the actual clustered key. So if it's a cluster table, if my base table is a cluster table, we always store our clustered key, regardless of how wide that clustered key is, in every non-clustered index. So the wider our clustered keys are, the wider our non-clustered indexes are going to be. Okay, there's no getting around that. Now, depending on whether we define that clustered index as unique or not, determines whether we store values in the root or the intermediate level pages. Okay, and I'll show you that example in a demo. And again, a non-clustered index, anytime we insert a record into our base table, we also have to insert that record in the non-clustered index. So any changes we make to the base table, we have to maintain those changes in our non-clustered index. So the more non-clustered indexes we have, the more we have to maintain on a data modification. So potentially, the slower our system can be. So you don't want to add many non-clustered indexes just because we have to maintain them. Okay? Now there is a caveat in that with filtered indexes, a filtered index is an index that it's always a non-clustered index, and with a filtered index, we have a predicate. We have a where clause whenever we define that non-clustered index. And whenever we define that non-clustered index, whatever records we insert or at index creation, we will put based on that predicate in our non-clustered, or in our filtered non-clustered index. So the filtered non-clustered index isn't guaranteed to have as many records as the base table, but a non-filtered non-clustered index will have as many records as the base table. Okay, so if I have to scan, if I do a select count against the base table, right, I don't necessarily have to access that base table to find out how many records are in it. I can absolutely go and scan to read all the pages in my non-clustered index to find how many rows are in our base table. So if you do a select star from table name, you're not guaranteed to scan that underlying clustered or heap. You can perfectly scan that non-clustered to find the number of records. Okay? For the non-clustered index structure, one second here. For my non-clustered index structure, very similar to my clustered index structure. It's still a B tree. The only difference, again, is that once I hit my leaf level, that leaf level only contains the non-clustered index key, so whatever columns I define my non-clustered index on, a pointer back to the base table, and if I have included columns, we'll store those in the leaf level as well. We don't store included columns in the root or the intermediate level pages. Okay? Those are the main differences between a clustered and a non-clustered. So a non-clustered is actually not part of the base table. We maintain it as though it was, but it's a separate index structure. That's why we can put non-clustered on their own file group. We can store them away from the base table, and because they have that pointer back to the base table, we can always access that base table. Okay. Included columns, these are added columns that we add to a non-clustered index for a specific purpose. The specific purpose is for covering an index. Does anyone want to explain what covering indexes are? And I have a Microsoft Power Stick that I will give away if someone wants to explain it. Yes, sir.
It includes all the columns that you would have in a specific query.
So the response was, it includes all the columns that you would have in a specific query. Absolutely. Yep, so come up after, and I'll give it to you after, okay? What that means is that if I have a select statement, and in my where clause, I am referencing the leftmost column in my non-clustered index, but my select statement has additional columns that I need to return that I don't have in my non-clustered index, I have to go out to the base table. So I traverse my non-clustered index, get to the values that I need at the leaf level, but my select statement says, hey, I need these additional columns. So I'll have to go out to the base table, get those additional columns, and then return them. That's called a bookmark lookup, or it's called a key lookup now. It used to be called a bookmark lookup. And depending on how many records I'm returning, that can be very, very expensive. Okay, but we'll talk about that a little bit later. Here's what an included column structure looks like. Almost exactly the same as a non-clustered structure, except for once we hit the leaf level, those included columns are only stored at the leaf level. So I can't seek on them because they're not stored at the root, they're not stored at the intermediate level, they're only stored at the leaf level. So it gets me a couple of advantages, okay, as compared to adding it just to the key itself. It allows me to get past the 900 byte limit that we currently have for indexes. Okay, so if you define an index and it goes over 900 bytes, SQL Server is going to fuss at you. It's going to say, we can't insert this record. Okay. Also, it allows you to store some data types in the included column that you wouldn't normally store in the index key, like blob columns, varchar max columns, invarchar max, those types of data types. You can store in the included column, but you can't store it in the key. So just some additional gains there. All right. Any questions before I switch over to a demo about the structures? Yes, sir. So the question was, what determines if you have multiple intermediate levels, the amount of data that you're storing? Okay. I'll show you an example of where we have no intermediate levels and where we have multiple intermediate levels, and it's just how much additional data I have to store. So good question. Okay, so let's look at a demo. All right. So what I'm going to do here is I'm going to look at first clustered index structures. So this is actually a very simple demo. I'll put the content out on the PASS website so you can go and download it, and then you can play with it. There's no special databases that you have to download for this particular, most of the demos that I'm going to show you today. So I'm going to create a demo, or a database called heaps.db, and in heaps.db I'm going to create a table called numbers table. Okay. I'm going to load some data into the numbers table. I'm going to load 40,000 records, and then we're going to look at some DMV information to see what's actually stored in it. Oh, I'm sorry. It's not showing, is it? Okay, 1 second. Thank you for that. Discard. Okay, sorry about that. So we're going to create a database called heaps.db, going to create a table called numbers table, and then we're going to load 40,000 records into our numbers table. And that's going to, at first, not do any type of index structure because we haven't clustered it yet. Okay, so let's just go up and create this. Should take just a second. It errored on me here. Oh, that's okay. Okay. One more time just to make sure I haven't messed anything up. Okay, very good. So I'm going to come down and I'm going to look at sysdm db index physical stats. And what this DMV is going to show me is you're going to use it in almost all of your index maintenance routines because this DMV is what tells me how much fragmentation I have in a given index. But it also tells me some other interesting information. I'm going to run this just for this particular table, and I see that I have 374 pages in this table. So 374 8K pages. It also shows me how many records I have. It shows me a page level. Now here my page level is 0. Okay? I don't have any other levels in this index, which means essentially it is a heap. It is a heap table. So we know at heap tables, we don't maintain any specific ordering. In previous versions of SQL Server, we had a command called dbccind that we could dump basically a given table structure. It'll show me the number of pages that I have in that. In SQL Server 2012, we made it so that sysdmdb database page allocations is a new function that will show me all of the pages and the linkages between those pages in a given table or index. So I'm going to run this against, and again, you don't need to know how to write this right now. This is going to be available as a download. So sysdmdb database page allocations, execute this. We see the allocated page ID, and this is in allocation order on disk. Okay, so 228 right next to 230, right next to 231. Now what's interesting here, our next page in our previous page ID is null. This is a heap. We don't maintain linkages for a heap. So there is no previous page. There's no linked list. Okay, so this shows you that the linkages for a heap just aren't there. We know which pages are tied together with an index allocation map page, but other than that, that's the only thing that keeps them together. Okay? So that's what a heap looks like under the covers. And there's additional columns of information that you can glean out of this particular DMV if you wanted to play around with it. Now I'm going to create a clustered index on this table, and I'm going to show you, instead of right-clicking and going to include actual execution plan, I'm going to set statistics XML on. It's just a different way to look at the actual execution plan. And the only reason I'm showing you this is that I'm going to show you what we're actually doing under the covers when we create this clustered index. Okay? We're scanning the table, which means we're scanning that heap table. Okay? We're sorting it because we have to maintain it in sorted order. Right? Then we insert it into a new clustered structure. Okay? It doesn't show you that we're actually getting rid of the heap under the covers, but this is what the execution plan looks like. So take the data, sort it, dump it into a new table, cluster it. Okay? Get rid of that. Okay, so now what I want to do, since now we went from a heap to a clustered table, our data is ordered. Looking at the same query this time, we can see that we have two structures now. Now we have a root page, and the root page is always the highest page level. Okay? So we have a page count of 1, and our root page is always how many pages? 1 page, right? So that's our root page. And what's interesting here is that if I scroll over, I can see that the record count for our root page actually has records in it. These are index records. These records point to the next intermediate level or the leaf level page. We have 374 records in our root page, and those 374 records point to 374 pages at our intermediate level page. Okay, so we have a root page, intermediate level pages all the way over to 374, and that root is going to point to them. Okay? Totally points to them. So if I need to access a given value in 2 IOs, root page, leaf level page, I have the data that I'm seeking for. Okay, so that's what a traversal in this case looks like. Okay, so here we're going to look at the same DMV as before, the replacement for dbccind, and here we now can see that we have linkages. Okay, we have our root page, and our root page doesn't have a previous or a next page because it just kind of stands alone. Then we have intermediate or our leaf level pages. We see that 648 is right next to 649. Let me zoom in a little bit here. 648 right next to 649, and we see that the next page, let me just fine tune it here, that the next page, 649, right next to 648. And because these are pretty much all right next to each other, these aren't fragmented. We'll talk about fragmentation a little bit later, and fragmentation is where the physical ordering doesn't match the logical ordering, so we have to go and jump around, and it really can hurt scan performance. But here, they're right next to each other, and because they're right next to each other, we wouldn't suffer any type of fragmentation problems. Okay, so this is the linked list. We always know where the previous page is. We always know where the next page is. Linked list, that's the sorted order that we have to maintain. Okay, so what I'm going to do is I'm going to go and grab, what am I doing here? I'm going to look at one of these intermediate level pages, or the leaf level. So let's grab page 648. So I'm going to use DBCC page. And DBCC page, you may have seen it in this session already here. What this does is you supply it a database name, a file ID, a page, and a type of verbosity level. And it's going to dump out the data in a given page structure. I'm going to use with table results because it makes it a little bit easier to see in our case, especially for a little bit later. So I'm going to run this. Actually here, sorry? No, you don't need that trace flag for table results. Let me see here. But I don't need table results here, so let's do DBCC trace on 36.4, 1. I think that's right. That should work. Okay, so we're going to dump this page out, and what I want to show you here is once we get to the end, we have a uniqueifier value, but it's not showing me. Let me have to skip this portion just real quick. Okay, I'm going to skip this portion. What I was going to show you, and I'll show you in the next example, is that I dumped the wrong page. My apologies. That's why I goofed up. It's early still, so apologies. So I dumped the wrong page. I was supposed to dump the root level page, so I'm going to dump 680. And if I dump 680, then I can show you. There we go. So here we have what's useful here is that we have a second intermediate result. When I ran it the first time against the data, and it depends on what type of page you're running this DBCC page against. I just ran it against the wrong type of page before. So what I wanted to show you here is this uniqueifier column. I didn't define my clustered index as unique, and we have to store that uniqueifier column. This is pretty much the only place you can see that. Okay, so we show you here, all of them are 0 except for that very first value. That first value is null, and the rest of them are 0. Now, had I inserted duplicate values, we'd increment that. Okay. But what's also interesting here is that this child page, so remember this is a root level page, and we have 374 rows returned in this root level page because we have 374 leaf level pages. This 648 points to a leaf level page. What I'm going to do is I'm going to go and dump 648, and notice here that this number value is our clustered key, okay? And it stores the value null, and because we store this in sorted order, it's actually going to store the value null. We don't have any nulls in this table, so it'll store the value 0 all the way up to 107. Okay, so 648, we're going to go and take a look at 648. Actually have it right here. Dump 648, and here we go. 648, you can see that, in fact, we scroll all the way down, stores all the way to 107. So it stores the value 0, number value 10, all the way up to 0. Well, we don't have 0, we have 1. You can see the uniqueifier here, but it stores those values all the way up to 107. So just going and looking at that page, we can see, because we store it in sorted order, 1 in our case, all the way up to 107, and this 649 will contain 108 all the way up to 214. That's exactly how SQL Server knows how to traverse those values. It knows exactly where they are because it always maintains it in logically sorted order. Okay, let's see here. So let's go and let's recreate the clustered index as unique. I'm going to use with drop existing. Recreate that clustered index. Go and take a look at the structure list. Nothing's really changed. We have new page IDs, but other than that, nothing has really changed. So I'm going to look at the root page again. And what I care about at the root page, 1096, is that we now no longer have that uniqueifier column. We defined it as unique. We need to maintain that uniqueifier column. Okay, and the same thing would be there for the leaf level pages. Now onto a non-clustered index. I'm going to get rid of this particular session, and I'm going to create the same table before. I'm just going to happen to call it heaps table, and in this table I'm going to store some additional records. Okay, it's going to take a couple extra seconds to run, but the reason I'm adding some additional records, we're going to create a non-clustered index on this, is so that I can show you when we have an intermediate level page. Should be done pretty soon. And I'm going to create a clustered index as unique so we don't have to worry about that uniqueifier value anymore. It's going to take just a little bit longer because we're adding more data. Now I'm going to create a non-clustered index on the same table. I'm going to do it on a different column. So before we were clustering on the number value column. Now we are going to create a non-clustered index on our bigger number column. The bigger number is essentially the number value plus 5 million. So nothing too interesting about the value itself. It's just another column. So create our non-clustered index structure. Now we're going to come down, see how deep our tree is. So the levels in a particular index is defined by, it's called how deep it is. In our case, because we added actually quite a bit of extra data, we added an intermediate level page. Okay, so we start at the root. Our root has one page, and it points to 7 records. There's 7 records in that root page. In the intermediate level, there are 7 pages, which are pointed to by those 7 records in our root. Okay? And those 7 pages point to 1,336 leaf level pages. Okay? So I can look at a value in this non-clustered index in 3 IOs. I can get all the way down to the leaf level by looking at the root, intermediate, and then leaf level. So a very fast way to access data. Okay. Here we're going to go and look at the linkages for that particular non-clustered index. And again, the thing to take away here is that we have a page level, 1 page for our root. We have, 7 intermediate level pages, and then it's going to show all of our leaf level pages. And we see the linkages between them. Okay, so we see that this particular intermediate level page points to 1952. And 1952 is way down here, so it's actually a little bit fragmented, which is perfectly fine for our case. We'll talk about fragmentation in a little bit. Okay, so I'm going to go out and I'm going to dump an intermediate level page. So let's go and grab 1632. And in 1632, what's interesting here is that we have the bigger number. Okay, and bigger number is our non-clustered key. We also store the number value. The number value is the clustered key. This is the pointer that goes back to the base table. In our case, it happens to be a clustered base table. We have to maintain that linkage. So anytime that we need to access additional columns to cover the query, we use this number value, and we'll go seek into that clustered index to find those additional columns that we need. Okay. Let's look at a leaf level page here. So let's go and grab. We'll look at 1600. Oh, I needed to look at a leaf level. Sorry, 1 second here. Let's find a leaf level page. That'll be 0. We'll get 1600. And here we can see that we have the number value and then bigger number. Okay? So nothing too fancy there. Whoops. No, that's perfect. Okay. So one function that is a pretty neat function is the sysfn physlock formatter function. And what you do is you pass in percent physlock. And what that's going to show me, and I'm forcing an index here because I want it to access this particular index, is that for a given index, it's going to show me the location of the record for that given value. So we can see that bigger number here, 5,000,001, is on file 1, page 1600, slot location 0. Now, why would this be interesting? Well, what's also pretty neat here is it has this key hash value. If I have a locked record, and I'm looking in, was it sysdm tran locks? For a given key value, we store that hash value as the resource description, I think. And I can use the value from that DNV to go and query against this function to see what particular record is actually locked. Okay, so I can use that key hash value to go and look that up, which is pretty neat. Okay, so I'm going to drop my clustered index, and in dropping my clustered index, I take my table from a clustered table to a heap table, which also means that any non-clustered index I have on that base table, I have to rebuild those, because currently they point to that clustered key. That clustered key is not going to be there anymore. We're going to replace it with a heap ID or a row ID. So I'm going to drop my clustered index. Okay. I'm going to come out here and I'm going to find just a particular page. So I'm going to use this function again. I'm going to find page 4352. So we'll look at 4352. Dump 4352, and notice here now we don't store that number value column in the non-clustered index. We have this row ID, which is an 8-byte value that points back to a unique row in our clustered table. So we actually had to rebuild that non-clustered index. We have a whole new set of index pages, okay, and we have this value that we have to point back to. Okay, so let's recreate it. Take just a second. And this time, I'm going to recreate the non-clustered index as unique. Now, what's interesting here is that whenever I create my non-clustered index as unique, now let's find an intermediate level page. We'll look at page 400. Whenever I define my my non-clustered index as unique, in my root and intermediate level pages, I don't have to store my number value. I still store it at the leaf level, but for a root or an intermediate level page, if I have defined my non-clustered index as unique, I don't have to store my clustered key on those pages. I still have to store them at the leaf, but not on the root or intermediate level pages. So a little bit of size gain there. Okay, so let's find a leaf level page. We're going to do leaf level. Just to show you that in the leaf level, we'll look at page 288. And in the intermediate level, we store the number value column. So we still have to keep it there. Sorry, not an intermediate level, in the leaf level. We still have to keep the pointer back to the base table in the leaf level, but if my non-clustered index is defined as unique, I again don't have to store it in the root or the intermediate level. I still have to store it in the leaf. Here, I am going to include a column. So I'm going to include the character column, which is just the third column that I have defined in this particular table. And what I'm going to do is I'm going to show you that once I include that column, I'm just going to recreate that unique non-clustered index. I'm going to find a page. Let's find a page, an intermediate level page, because we don't store we don't store included columns on the root or the intermediate level pages. So let's find here. And notice we have a lot more intermediate level, or we have a lot more pages now because we've included that column. So we'll see 5720. And we do not store that included column on 5720. However, if I find a leaf level, let's find 5496. For 5496, sure enough, that included column is at the leaf level. So included columns, no reason to store them at the root or that's the main benefit. We're not storing them at the root. We're not storing at the intermediate level. They're just there to cover queries. Here we're showing it that at the leaf level, indeed, we do have the included column there. Okay. Any questions about what we just went over? I know we went through a fire hose mode there. Yeah. I'm not sure if we've documented it or not, but you can use it. It's not going to hurt anything. Other than it has to scan the data structure. You in the back. So the question is there any benefit to adding an identity? Is there any benefit to adding an identity column to my non-clustered index to define it as unique? I'm going to say it depends, right? But it depends on your circumstance, not necessarily. But I guess it depends. Yeah, I can't say that there would be. And also, I want to say no, but I mean, there probably are use cases where it could, but off the top of my head, I want to say no.
Would it depend if you had a clustered index?
Yeah, it's going to depend on a lot of things, right? Would row or page compression change any of the results we're seeing? That's a good question. I haven't tested it with that. I don't know the behavior of DBCC page on compressed value, so I want to say no, but I would have to see it because we will go and decompress those pages once they're in the buffer pool and we're accessing them, and everything we access has to go through the buffer pool, right? So I'm thinking that the behavior would be the same, but I don't know for sure. Okay. Okay. Yep.
Wouldn't that decrease your feature depth potentially if you're compressing the pages for the index leaf?
I'm sorry?
The follow-up to the question the gentleman.
Yeah, that's the thing. I'm not completely sure if it's going to return the same results or not. So.
I wasn't asking about DBCC page. I'm talking about the allocation on disk, right? I have less pages to store, so potentially the index depth is going to decrease.
Yeah, I mean, we're going to store more values on a page because of the way that we dictionary compress it than we row compress for sure.
So I had a quick question about filtered indexes. Is there an overhead incurred for the maintenance of filtered indexes if the underlying value changed in the base table doesn't qualify for the predicate?
No, because it wouldn't match the predicate. So the question was, for filtered indexes, is there an overhead for changing the underlying values in the table if it doesn't match up to essentially the predicate on the filtered index? And it wouldn't, right? We'd have to check to make sure that it didn't, but other than that, no. I'm going to go ahead and keep going because we're about 40 minutes in and I want to make sure we get done. Okay. So on to statistics. You may be asking yourself, well, this is an indexing talk. Why are we talking about statistics? Well, statistics play a huge role in whether we're going to use a particular index or not. So a statistic is just basically a sampling of data in a given column. Okay, whenever we create an index under the covers, we always create a statistic associated with that index. When statistics get out of date, we'll either update them ourselves, so we'll update them manually, or we'll rebuild our indexes, or we have update statistics command that'll get kicked in behind the scenes if we have that setting set on a given database. But the main thing to take away with statistics is that as our data changes, these statistics get old, and the optimizer relies on these statistics heavily to make its decision of how to access data. Okay, so if our statistics are way out of date, it may choose one plan versus another. There are certain constructs in SQL Server that we don't maintain statistics for, like table variables. We always assume one record in a table variable, and if we're joining a table variable to a very large table, it may make some assumptions based on the fact that we're just using a table variable. So something to keep in mind there. So out-of-date statistics can absolutely lead to suboptimal execution plans. How do we view statistics? Let me see if you can see that okay. Let me zoom in a little bit here. So DBCC show statistics is the best way to view a statistic because you're able to see the histogram for a given statistic. Here I'm using DBCC show statistics and I'm passing in the table name. Here we're running against sales order detail and the particular index is product ID. I am showing the stat header and the histogram. I could also show the density vector. I don't actually have to include a with statement. But what this is showing me is that here is my stat header, and it's going to show me how many rows are in the table, how many rows are sampled, how many steps we take. Steps are essentially the number of steps in the histogram or our sample points. Right now we'll take at most 200 steps. Okay, we may take less, but at the most point, we'll take 200 steps. This is the histogram. The histogram is the actual record values. So here, this is on the product ID column, and this range high key is essentially product ID value. So this is product ID 730, this is 732, 738, and so on. Now what's interesting here is that without even having to access that base table, I know that between 732 and 738, there are exactly 154 records that match up to that range. Okay, it does not include 732 or 738, so values 733 through 737, there are exactly 154 records that match up to that range whenever we took that statistic. Okay? We know that for the value 741, between 738 and 741, there are exactly one row or one distinct value between that range. And that makes sense because there's only one value there's two values between 738 and 741, 39 and 40, okay? But there's only one distinct value that matches up to that. So without even having to access that base table, SQL Server has a pretty good representation of how much data we're looking at for a particular value, okay? And if we were actually to run over here, let me move over here, and look at this query against this base table, between the values 732 and 738, grouping by product ID, we can see that there are exactly, between 733 and 736, there are 154 records. Well, we were just looking at that right here. Between 732 and 738, there are 154 records. So SQL Server, without, again, actually having to access that base table for certain predicates, knows exactly, or at the time that the statistic was created, how many values that are going to match up, assuming it was a full scan. So we in a lot of cases, will take less than a full scan, so we didn't touch all of the values in the given index, but it's a good representation of what SQL Server has to deal with for a given predicate. And the optimizer relies on that very, very heavily. Okay? So let me, okay. So what I'm going to do, let's look at our options here. So, sorry. Our database options for maintaining and creating indexes. So we have an auto create statistics database level option, which means that at any point in time, if SQL Server sees a query that has a predicate or a where clause where we do not have an index on that particular column value, behind the scenes, we'll go out and we'll sample the values in that column and we'll create a statistic behind the scenes. Okay, those statistics are prefixed with underscore WA, and that's because whenever that code was written, the developer that was writing that code lived in Washington, and that's what they're prefixed with. And okay, so that's how you see some of those statistics inside of your database engine. Okay, SQL Server saw a column of interest and thought it would be useful to go out and create statistics for that particular column. Sorry? Yeah, those statistics are persisted, yeah, just like a regular statistic that was created under an index. You can also create them by hand, so those are creation options. Auto update statistic is whenever we have a recompilation threshold, so whenever, assuming it's a large table, 20% of the table has changed since the last recompilation, and I think 200 records, we will go out and we'll run update statistics behind the scenes with usually a smaller sample rate. Update statistics async, exactly the same as auto update statistics, except for depending on the query that's changing, that it's hit that recompilation threshold. So maybe I'm running an update statement and it hits that recompilation threshold. If I just have regular auto update statistics on, that query will wait until we go and update the underlying statistic, and then it'll use the new statistic. If we have auto update async on, that query that caused that recompilation threshold will actually use the old statistics, and behind the scenes we'll go and update the statistics. So any new queries that come in, it'll have the new statistics. So the reason that's in place is that there are some cases where the query that caused the recompilation threshold has to wait a long time for the sampling, and so that's why async is there, right? Sorry? Okay. I don't know. Was that a question or you're saying? Okay. I haven't tested that. So the question was, is there a magic background test that does it, or it's the next query? I would say we have a background test that does it, but I would have to verify. I'm gonna keep going just because I'm running a little short on time. So what are your best practices here for statistics? Typically, use the defaults unless you know you need to do otherwise. For large data warehouse environments, those are typically the exception, because if auto update kicks in, it may take a really small sample rate, and if I have a wide data distribution skew, then having that small sample rate may affect my query plans in a negative way. Okay, implemented a trace flag, 2371, that can basically change that recompilation threshold. And the reason that is because for really, really large tables, it may take a long time to hit that recompilation threshold. So using 2371 will basically make that recompilation threshold much less. Okay? Okay, so let's take a look at out-of-date statistics and how they can affect us. Okay, so what I'm going to do here, I'm just going to create another database called StatsDB. I'm going to set auto update off. I'm going to create a table called stats table. I'm going to cluster that table, and then I'm going to insert 10,000 records into it. Whenever I insert those 10,000 records, I'm going to get a hash value of 10, so I basically have an even distribution between the values 0 and 9, and I'll have about 1,000 records for each one of those values. And I'm going to show you the values that we have. Okay, so let's see. Selecting against this table, group values 0 through 9, there are 1,000 records showing up for each group value. Now what I'm going to do is I'm going to modify almost all of those group values for the value 5, and I'm going to set it to 3. So I'm essentially changing my data distribution, right? Change that, run the same query, and we can see that now for the value 3 we have 1,999 records, for the value 5 we have 1 record. Now what I'm going to do is I'm going to create a non-clustered index with statistics no recompute on, which basically says unless I'm rebuilding that index or I update that statistic manually, don't maintain those statistics. So I'm going to recreate this. I'm going to create this index. And now if I'll just right click and look at the actual execution plan. Running this particular query against this table, I have this lookup value column. I don't have this lookup value in my non-clustered index. That's why I called it lookup value. So it's going to show me that I have a bookmark lookup. So in a bookmark lookup, here we can see that we seeked into our non-clustered index. We got the record that we needed, and then we went out to the base table to get that value. And if we hover over this and look at actual versus estimated number of rows, actual number of rows 1, estimated number of rows 1, and that's a good thing because they're exactly the same. Okay? So now I'm going to skew things a little bit just to have a little bit of fun. So we can look at DBCC show statistics, and we can see that in show statistics we have 10,000 records in our table. We have one value, looking at this equality rows here, that matches up to the group value 5, and we have 1,999 rows that match up to the group value 3. Okay, so our statistic that we have matches up exactly to the values that we have in the underlying table. And that's a good thing. Now what I'm going to do is I'm going to skew that. So I'm going to insert 10,000 more records, all for the group value 5. And when I do that, things are going to get a little hairy for me. Okay. Do that real quick. Now looking at DBCC show statistics again, we still have one record that shows up to the value 5, even though in the underlying table we have around 10,000 records that show up to the value 5. Okay? Looking at the value 5, sure enough, we have 10,001 records show up to match it. So a very weird data distribution skew. SQL Server thinks there's one record, but in actuality there are 10,000 records. And that will affect our query plan. So if I come over here, and first we'll look and see how many pages are in the clustered index. In our clustered index we have 82 leaf level pages, okay, and we have one root page. Okay. Now the reason I'm showing you this is because we'll leave off the recompile for right now. I'm going to run that same query again. We're going to look at the actual execution plan. We already have that on. Looking at the execution plan, we still have an index seek with a bookmark lookup. But if I hover over here, actual number of rows 10,000, estimated number of rows 1. SQL Server thought it was accessing one record, but in actuality it accessed 10,000 records. Because it thought it was accessing one record, it chose this bookmark lookup. Okay, but in fact, it had to go out to that base table 10,000 times to get the additional lookup value column that it needed. Now, I haven't talked about statistics IO yet, but if I run that same query again and I set statistics IO on, what this is going to show me is the number of pages that are touched in the buffer pool to run a specific query. In a lot of cases, That's going to be your best option for determining whether when you're tuning queries, whether you're making headway or not. So what I'm going to do is come down here, run this same query again. Okay, execution plan is the same. Looking at the amount of I/O, we have 20,000 logical reads. There are only 84 pages in this table, but we had to touch over 20,000 of them. We had to touch the same pages essentially 20,000 times because of that bookmark lookup. SQL Server thought it only had one record to access. It had to access 10,000, so it had to hit that non-clustered index 10,000 times, go out to the base table 10,000 times. That's why we have that 20,000 logical IOs. Okay, a very simple query that got expensive on us. Okay, so what do we do to change this? Well, we could try to use recompile, but recompile will only recompile the values that we have, so it has nothing to do with statistics. So if I use recompile, still have the actual number of rows, 10,001, estimated too, so in our case, estimate's even off. Okay, come down here, the only way to really get around this, the easiest way to get around this, is to rebuild that index. Rebuilding that non-clustered index, running that same query again, or looking at the statistics first, we can see that now our statistics are up to date. Okay, first time when we ran the query, when our statistics are off, we had an index seek with a bookmark lookup. It was very expensive. Now, running that same query again, we just scan that underlying table. And in scanning that underlying table, we have 84 logical IOs. So in this case, it was much more efficient to just scan the underlying table than it was to seek. So a seek is not always faster than a scan, for sure. All right. Just running short on time here, so I'm going to kind of go through this. So index maintenance, talk about fragmentation and what that actually means. So page splits. Again, a record must always fit on a specific page, okay? And if it can't fit on that particular page, we essentially have to split that page. So we have to create a new page, load data on the, half the data onto the new page, and then our linkages are kind of mismatched. Okay? So this can be resource intensive. We have to generate a lot of transaction log, and so there's overhead there. Okay? Here's what, and this leads to logical fragmentation whenever we have a lot of page splits. So this is where our index and data pages are not physically and logically aligned. It can hurt scan performance, but usually doesn't matter too much for seek operations. Okay? So here we have the value 10,001 to 1,000 has to jump over to 1,001 to 1,500, and just a looping operation here essentially because those pages are not physically next to each other. Page density, this is where a page is not full. You specify this with the fill factor setting whenever you create a particular index or you rebuild an index. So how full it is, the more full a page is, the less likely we can fit a record onto the page, which may cause additional page splits. But the less full a page is may lead to bloated plan cache. So we load a page, even if it's 10% full, into the buffer pool, which means that we have 90% of the space wasted on that page. So there's a fine line between page splits and page density. Do what's right for your environment. When does fragmentation matter? Typically for singleton lookups, so if I'm just looking for a couple of records, fragmentation doesn't really matter. Okay? There's large shops out there that have really, really large tables, and because they are an OLTP environment and they're only looking up a couple of records at a time, they don't even bother with rebuilding their indexes. They only update their statistics, and that's all they need to do. Okay, so, but it matters most for scanning purposes. For warehouse environments where I have to scan, it can inhibit read ahead. Okay, so that's something to keep in mind there. The main thing to take away from that is that if my index is very, very fragmented, there's a good chance that my statistics are out of date. Okay, whenever I rebuild my indexes, rebuilding my indexes gives me a fresh full scan of my statistic, and then because I have fresh statistics, my queries that touch that index are going to recompile, and I may get better plans because my statistics got updated due to me rebuilding my indexes. Okay. So I'm going to look at this demo of fragmentation right after I get through these slides here. So rebuilding an index, what are my options? Okay, so I have, for rebuilds, there are very few cases where I need to drop an index and then recreate it. Dropping it takes it offline so that it's not there, and then I have to go and separately recreate the index. Typically, I want to use alter index rebuild. Okay, I can use alter table rebuild for heap tables. What alter index rebuild does for me is that for a clustered index, I don't have to go and touch my non-clustered indexes. Okay, it's just going to, because of that relationship between my non-clustered and my clustered table, because of that value, that clustered value between them, if I rebuild my clustered table, I don't have to touch my non-clustered indexes at all. Okay, if I dropped my clustered index and I recreated it, then I do. I have to rebuild them twice. Okay. For offline index rebuilds, we have to basically take that index offline during the operation. We have online index rebuilds where we'll take a schema lock at the beginning at the end so we can swap it over. Basically, an online rebuild rebuilds an index in the background in parallel. We'll use read-committed snapshot isolation to still be able to access that index while we're rebuilding it. Alter index all will go and rebuild all of your indexes on that table in index ID order. Okay, so we'll start with the clustered index first because clustered index always has an index ID of 1, and then any non-clustered index after that, depending on the order that we created them, we'll rebuild them in that order. Drop existing, this is part of the create index syntax, and what this is going to do is it allows me to change my underlying structure of my index. So the benefit I get here is that if I do a drop existing when I am changing the structure for a clustered index, I only have to rebuild my non-clustered indexes once. Okay, I don't have to rebuild them twice like I would do if I had to drop the index and then recreate it. So great for changing the index definition while I don't have to go explicitly drop the index and then recreate it. Okay. Index reorganization. This is another way to remove fragmentation. The main difference between index reorganization and rebuilding is the fact that with a reorg, we don't update statistics. Index reorganization is an online operation. We'll basically look at 8 pages at a time, compact those pages together, and then we'll kind of like a sliding window. So with a reorg, you're not guaranteed to have new pages. With a rebuild, you're going to have new pages every time. So we're going to go and create a totally separate structure, load new data into that structure, and then we'll swap out and we use that new rebuilded structure. With a reorg, it's an online operation, so that if I stop halfway through a reorg, any work that I have previously done, I get to keep it. With a rebuild, it's an all or nothing operation. So if I stop a rebuild halfway through, any work that is done is rolled back. If I stop a reorg halfway through before it's touched the entire table, any work that I've done I get to keep. But because we're not guaranteed to touch every page in that table, reorganization does not touch statistics whatsoever. Even though potentially it could if we ran through it in its entirety, we're not guaranteed to, so we can't. Okay, it removes leaf level fragmentation. We tried to establish the original fill factor, but it's always single threaded and it's always an online operation. Okay, it's always fully logged. Index rebuilds can be minimally logged. Okay, and I'll talk about minimally logging in my log internals talk after lunch. Okay. So when should I do what? When do I rebuild versus reorganize? The common wisdom is that if it's less than 30% logically fragmented, then I reorganize. If it's more than 30% logical fragmented, then I rebuild. The reason for that is that reorganization, depending on how big my table is and how fragmented it is, can require a lot of extra work. A rebuild is a fixed cost. Okay, so I have to perform the same amount of work whether I'm 1% fragmented with a rebuild or I'm 99% fragmented. It's still going to have to do the same amount of work. With a reorg, depending on how much fragmentation there is, there may be a lot more work to do. Okay, so if it's less than 30%, reorganize and then go update your statistics. If it's more than 30%, just rebuild and you don't have to worry about going and updating your statistic. The answer really is, it depends. Do what works for you. Your mileage is going to vary depending on your scenario, depending on your workload. Do what you need to do there. Okay? So in summary, reorganize, always an online operation, can be stopped and you won't lose any work that you've previously accomplished. Never update statistics. So if you reorganize, you need to go and update statistics yourself. can generate a lot more transaction log activity than a rebuild, just because, and that depends on how much work it has to do, right? So assuming a really large table, 99% fragmented, we're going to have to do a lot more work to reorg that table than we're going to have to do to rebuild it, just because there's more work to do. And again, rebuild's a fixed cost. With a rebuild, it's an all or nothing operation. And so if you roll it back, if you stop it, you lose any work that you've done. We will update statistics with a full scan always, except for, there's one caveat to this in SQL Server 2012. If you have a partition table, you're not always guaranteed a full scan, but it'll be really close. It's going to involve some sort of blocking, even the online operations. There's really no getting around that. But the online operation, even though it takes a little bit longer and is a little more resource intensive, usually is a win because it involves a lot less locking. Okay? And it can be minimally logged. So if I'm in the simple or the bulk logged recovery model and I perform a rebuild, potentially there's going to be less transaction log generated just because we're only touching the allocation pages. Okay, so let's take a look at a couple of demos here. And we have 10 minutes left, so we may be pretty good on time. So let's first take a look at fragmentation. So what I'm going to do here is I'm going to create another database with a numbers table. I'm going to put a clustered key on that number value column, and I'm going to create a non-clustered index with a fill factor of 100 on my bigger number column. Then I'm going to go out and I'm going to insert some records into this table. I'm going to insert every third value, I'm going to skip it. Okay, so I'm going to insert the values 1 and 2, skip 3, insert 4 and 5. So whenever I insert this data, my pages are going to be full. So if I just run this real quick, I'll insert it. My pages are going to be full, and then I'm going to go back and I'm going to insert every third value. So I'm going to have to perform a lot of page splits. I have to perform a lot of page splits, and my table is going to be almost 100% fragmented. So if we just look at the value in this table right now, have the value 1, 2, we skip 3, 4, 5, and so on. Okay? Our fill factor is at 100%, which means our pages are full. Hold off on your question. Come ask me afterwards because I'm running a little bit low on time. So now I'm going to run the same insert as before, except I am going to insert every third record. Okay? Look at the level of fragmentation, and we can see that we're almost 100% fragmented. Okay? Now, I have written this very fancy way to visualize fragmentation. I can use this database page allocations DMV. I can use new windowing functions in SQL Server 2012 to basically look to see if my previous page matches my current page and my next page matches my current page in that linkage order. And so it should match up very, very closely to what the fragmentation level that's returned from index physical stats. Okay, so there's a couple percentage points off there. There's some edge cases that I'm not taking into account with this particular query. Okay, so just taking a look at database page allocations, we can see that 272 physically right next to 278, but 272 points to 2296. So I come all the way down to 2296, if I can find it here. 2296, and that points all the way back up to 279. So that's fragmentation. That's what it looks like. There's a way to visualize that. If I look for a single record, let's turn stats.io on. If I look for a single record in this table, okay, one record return, looking at the amount of IO generated, 3 logical reads. We have a root page, we have an intermediate level page, and we have a leaf level page. That's 3 levels, 3 IOs. We found the record that we need, and it doesn't matter that we're fragmented. Right? However, if we go and we scan that table, I'm looking for a pretty large range scan here. We return 242,000 records. The amount of IO generated, 887. Okay? 887 pages touched. Okay? I'm not going to look at that right now. I'm going to go and rebuild that index. Now, if I rebuild that index and I come down and I look at the fragmentation now, we're at 0% fragmentation. We have around 684 pages in this table. If I go and look at my pages now, 4312 is right next to 4313, which is right where it should be. No more fragmentation. Okay? If I run the same seek operation as before, we still have 3 logical reads. So that didn't change whatsoever. Okay? But because we have a different number of pages, we have to scan a different number of pages. I'm not going to look at read ahead right now, but our read ahead was affected. We actually scanned a lot fewer pages. Okay, so just fragmentation there. All right, so I'm going to skip the page density fragmentation just because it's kind of a convoluted demo where I'm going out and I am setting the fill factor for a particular page to 10%, loading the data, and then showing you that we have a lot more pages just because I set it to 10% and we have to generate a lot more pages. So what we're going to do now is I'm going to prep these two demos. We have just a few minutes left. I'm going to prep these two demos, and then we're going to finish up the slides, and then I'm going to show you exactly what these demos are doing. So I can show you the contrast between a rebuild operation and a reorg operation in terms of how much transaction log is generated for a really large fragmented table. Okay. Come back out to the slides, and then we'll finish up here. Okay, so SQL Server 2012 index changes, we can now perform rebuilds on blob columns in an online fashion. We couldn't do that before, so if you have indexes with included columns that are varchar max, in varchar max, blah, 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 we can rebuild those now online, okay, in SQL Server 2012. Online rebuilds of partition tables don't always result in a 100% sample rate, but they'll be really close. And the reason that they don't always result in a 100% sample rate, some of the things that had to change for the additional number of partitions that we allow on a given table. SQL Server 2014 index changes, online operation lock priority. So in some cases we have blocked operations because it's an online rebuild, and we'll allow you to set the priority of those rebuild operations. I don't have a demo for that. We have new hash indexes in Hekaton. Okay, and this has to do with the new Hekaton engine in SQL Server 2014. And I can create a named non-clustered index that is not associated with a constraint whenever I create a table. Okay, it's going to be in the actual create table definition, so I don't have to create a table and then have separate create index statements after I've created my table. I can do it all in one fell swoop in the actual index creation. Okay, so let's jump back out here. And we'll look at the demo that we had. So what I'm looking at here is I've created two separate databases, and in these two separate databases, I have a table called sales. In the sales table, I have a unique identifier column, and I am defaulting it to new ID, which basically, whenever I've loaded the data into this table, okay, whenever I've loaded the data in, it's going to be really close to 100% fragmented just because the general nature of how GUID columns work. Okay, they're random in nature, and so by the end of it, we're going to have two databases with a sales table in each one that are very fragmented. I've then created a clustered index on that GUID column, and then I've inserted from the sales order detail table 4 times into my sales column. Okay, I've came down, I've created a full database backup and a log backup because this is in the full recovery model. I'll talk about in my log talk why I did this specifically. And now we're at a point where we're ready to look at the amount of fragmentation, or sorry, the number of log records generated. In SQL Server, anytime we make a database change, we have to generate a log record for that because of our write-ahead logging protocol. So at this point, both of these databases should have, this query should be returning 0, okay? And the only reason for that is because I've performed this log backup. In the full recovery model, a log backup will truncate the log, so we don't have any transaction log records associated with that. So in both cases, we are at 0. So what I'm going to do is I'm going to kick off a reorganization of this large table here, and I'm going to kick off a rebuild of this table here. Okay, rebuild's complete, our reorg's complete. Now if I look at the amount of transaction log generated, I'm going to kick this query off for our reorg, come over here and look at our rebuild, we'll see that we have 8,200 transaction log records generated for a rebuild. Is that good? Is that bad? It's in a vacuum. It's hard to say. But coming over and looking at the reorg, we have 545,000 transaction log records generated. Okay, we're in the full recovery model. A reorg's always fully logged. It had a lot more work to do. The rebuild is fixed cost. The reorg totally depends on how big the table is and how much work it has to do to defragment it. So a lot more transaction log happened to be generated here. Okay? So finishing up, is there any questions before we call today? Come up afterwards. Feel free to. Resources, I have a resource slide here. Session evaluations, please go fill out one if you don't mind. Thanks everyone for coming. Thanks. We finished right on time. Feel free if you have additional questions, come up and ask me. I'm happy to answer them as long as you have them.